Okay, so the question was on homework 4, and you're not the only person who had this question. There were similar versions of this question, so I figured I would go ahead and answer it. Or, let's say, give you some advice on what you might end up with, okay? So let me pull up the homework, and let's read the problem statement together. Let me not pull up the solutions page. Almost did it. Okay.
Feel free to email that out.
Yeah, feel free to just email that. I've done stuff like that before. It wouldn't be the first time I made a mistake like that. Okay, so you've got this random sample voltage regulators, and we already determined this was based on the binomial distribution, okay or not okay, right? Defective or passed. And we know that our process defective rate, proportion defective, right, should run at or below 3.5%. And so the question is, am I correct that for assessing the process capability for attribute charts, we just have to compare the data to target? And yes, that's true. But here's the question: what are you going to compare? This is kind of like a critical thinking type of question, which is good for a graduate school, right? But let's take a look at that. So let's say you have this attribute chart. That's your upper control limit. This is your lower control limit. And this is going to be your average, right? And so if we're using a proportion chart, it's P bar, right? Average proportion. If you're using an NP chart, it would be, NP is a count, right? So it would be your average count defective, one of those.
This is our control chart?
Yeah, this is our control chart. And I'm going to, okay, just pretend that's in control.
Why does it look like that?
It doesn't look like that, okay. But let's just say this is in control, symmetrical, everything that we want it to be. So if I'm looking, let's do this a little bit differently. Let's say, just for fun, that my P bar is at 2%, okay, or 0.02. Let's just say that it's there. And my upper control limit is at, for fun, let's say it's at 5% or 0.05. Okay, so let's say that instead of 3.5, let's say the upper spec limit, they want it to be at or below 2.3%. So I'm just going to say this is 3% here, this is 4% here. And I'm going to say these go up a little bit higher, okay? So I could say, all right, on the average, am I below what the expectation is with respect to average proportion defective?
Yes.
And the answer to that is yes. However, would I expect to see some days where I might have a proportion above that? The answer to that is yes. So evaluate your data in light of that, because that is going to be what's critical. Because you don't get to choose. I mean, you're going to send everything to your customer. And then you say, hey, on average, we're OK. And they're like, yeah, except that on this day that you sent us this, you gave us 5% defective, and we're really angry with you. So that's something to consider, too. Now, the other part of this is calculating a CPK equivalent, right? CPK equivalent. And what we do for a CPK equivalent, and of course, when we're looking at a regular CPK, right? We're looking at whatever's closest spec limit to the mean and dividing that by 3 sigma. So we're looking at half curve widths. But what this really relates to is your percent out of spec related to that closest spec limit, what you expect to see for your percent out of specification, either on the high side or the low side or both. So what we do with the attribute data is like, all right, and we can only do this for binomial data. It doesn't really work for the Poisson data. but it does work for binomial. Since we know what the proportion defective is, it's kind of similar to saying what's out of specification. So if we had continuous data, and here's my lower spec limit, upper spec limit, and I had this curve, I'd have some proportion out of spec or proportion defective, right? And so this is similar to proportion defective. So I take that information, that proportion defective, I can pretend that that's my area that's out of specification, and then back calculate the z-score and divide it by 3. So if you remember, CPK equivalent equals your z-score divided by 3. Do you remember that? And a z-score is some x value minus mu over sigma. So if we take that z-score and divide it by 3, it looks x minus mu over 3 sigma. Just kind of like this. This would be x. This would be mu 3 sigma. Make sense?
What do we use for the proportion defective? the average.
That would be a good place to start. Okay, so if I had an average proportion defective of 2%, I can merely go to my z-score, come back here and put in 2%, take this and divide this number by 3, and it gives me an equivalent CPK. Okay, now for you to be, here's a good question for you. What would you have to, in order to be capable at a minimum of 1.33, what would that z-score have to be? Well, you'd have to make it so it's 4 divided by 3, right? So that z-score is going to have to end up being 4. And in order for you to get 4, you're going to have a pretty low proportion out of spec. Oops. Okay, something similar to this. We'll just keep going like that until you get... Oops, it should be 3, sorry. So something around the 3 area, and actually it ends up being close to that. Oh.
You switch it so you can put in...
What's that?
Switch one of those so you can just put in Z and then get the %.
Yeah, I think so. Well, thank you. Okay, so 0.0032%. That's what you'd have to have. That's a low percentage defective rate. So I just want to make that kind of clear. We're not really comparing to the 3 point. There's 2 ways you can do it. Okay, one is to compare to whatever, and that's typical for businesses to say, okay, in any shipment we don't want to see more than 3.5% defective. Whoever's online, could you mute your mic for me, please? Okay. Oh, it's just Jeff. Okay, hi, Jeff. Sorry about that. So you can compare to the standard, but you could also look at the CPK. I mean, really, to be considered capable by the standards of having, 4 sigma capability, you'd have to have a really low proportion defective. Yes.
Can we rewind a little bit?
Yes.
Capability. So since we have, in this example, equal subgroup sample sizes of 500 each, we can use an NP chart, right?
You can use an NP chart. Yep.
Okay.
You can use an NP chart and then figure out what your proportion defective is on average. I just put P down. You could use either one.
Okay.
And you know from your flow chart that either one is fine. Some people relate better to counts. Some people relate better to proportions. So if you have the option, you have equal sample sizes, then that's fantastic.
Right.
It's been my experience that I never had equal sample sizes when I was doing proportion defective and measuring that type of data in manufacturing. Never. So I never got to use an NP chart, but I would have really liked to.
How come you can't use the Poisson distribution, the estimated distribution to figure out that percent out of spec, but you can for binomial?
Well, you'd have to make it because you're looking at proportion defective versus defects per unit.
Oh, okay.
And so I don't know exactly how to relate defects per unit, because sometimes you can have defects per unit and we don't consider it defective. You know what I mean? Like I could have a couple of tiny ink smears per can, and I'd be like, yeah, it's not really conforming, but it's not. You know, I do the Larry Wagner test when he would bring me a can of water and say, does this can will it hold beer? And the answer to that is yes.
You can use a normal distribution.
We're just trying to get an estimate based, and the reason why is because we're trying to make it similar to the proportion defective, proportion out of spec. We're making a relationship there. But that's why they call it equivalent, because it's not perfect. But that's the story with that one. Although, if you want to talk to Ryan Witt, he tried to make it happen. Yeah, he tried to make it happen, but I couldn't find a way to make sense of it. None of the literature does it that way. So Ryan is a math enthusiast to the extreme. Hardcore. He has his own blog. I don't know if you knew that or not.
Didn't.
Okay, yeah, he's got a blog, and he shares code.
Oh, I'm going to ask him about that.
Yeah, well, yeah. He and Mike Burr are two peas in a pod.
I was going to say, it sounds like Mike should have a blog.
He may have a blog. He may. Okay, let me make sure I answer everyone's questions here.
Sorry.
So Tyler, no, you're fine. Tyler, shouldn't those be the upper spec limit and the target 0? Correct.
I just phrased it differently.
Yeah, it's the same type of question. But yeah, when we're talking about defective, obviously you don't want to have anything defective. I mean, think about Afton's bag of Cheez-Its here, which looks amazing. We don't want even one bad Cheez-It in there. That would make one nasty Cheez-It in there would make the whole bag defective. Or like an apple, like a cinnamon apple flavor, something in there, just totally make it disgusting. Okay, Josh, yes. Is that comparing the mean to the target or each sample value to target? So take a look at the upper spec limit, what you get for your control chart, because that's the range of variation you could expect. We expect 99.73% of the data to fall within that in the upper spec or upper control limit and the lower control limit. So you would have to see not just where you're running on average, but where the process is running, how high it might absolutely get. Okay, so P-bar to target, yes, you compare P-bar, but also look at the whole process. And so for CPK, no, we just talked about that, Chris, and we don't have to use the binomial in there. Well, hold on. If so, is this because unlike using another one, using binomial? Okay, I think maybe I explained everything here. I'm going to have to go back and read through everybody's stuff here. But just so you're aware, if we're back calculating on the CPK, I just went through how to do that. And when I mean back calculate, and I probably should have said CPK equivalent. It's my own jargon I developed. Okay, let's get started tonight. Realize this is kind of messy here. Discard, let me get rid of this. All right, we're going to talk about discrete measurement system analysis. So last week, we finished up our study on measurement system analysis for continuous gauges, okay, or continuous data that comes from gauges. Now we're going to look at discrete measurement. And of course, you guys are familiar with discrete. There's two parts of discrete. One is for nominal, and the other is for ordinal. Right? So nominal is kind of mean in the discrete sense means a name, right? Nombre. That's how I remember it. But you'll notice that there is some reading for you to do on the website. This is the book. Okay, I'm just letting you know that this is the thickness of the manual. This, what I'm giving you tonight, and probably will go into our next lecture after fall break, is kind of an introduction to this, because this is a lot, right? I mean, this could be a whole class just doing this, right? So I'm going to teach you how to do this, but there's probably more to be understood. This particular technique that we're using is going to be for nominal data applications. So this is associated with good or bad, okay, not okay, pass, didn't pass, stuff like that. There's other techniques for ordinal type of data, and after you see this, just understand that the ordinal techniques are even more challenging. So, and not saying that this is challenging. This may be something you just get right away. But what I've noticed, at least with technical folks, including myself, we're so used to the arena of physical measurement and physical things. When we get into something like this is more in the area of social science applied to physics. That is kind of like, whoa, okay, wait. Nominal and ordinal is something we don't deal with all the time. So we're going to talk about measuring agreement. And the interesting thing about this, we're measuring how well these nominal, whether it's a gauge or a person, how will they agree with an assessment on something. So if I am looking at, I had this great gauge. It was called the Presco Vision System. And I could send good lids through there or bad lids through there. And if it was good, it should tell me it's good. I was the expert. I knew it was good and what was bad, right? So I had to assess whether or not it agreed with me. Did it call a good one and a bad one or a bad one? Or did it call some of the bad ones good ones, which I didn't want? Or some of the good ones bad ones, which I also didn't want? Two different results that would come from that. So we're looking at measuring agreement, and believe it or not, it's a little bit more challenging than measuring disagreement. So we'll look for procedures for measurement system analysis on the gauges, and then there's different types of situations you may run into where you have two appraisers and two categories, and we'll talk about what these metrics mean, Kappa and Kappa max. Because these are measures of agreement right here. We use these statistics for agreement. And I believe Cohen is the one who came up with this. If you're interested in the history of statisticians, they always name it after themselves. No ego involved there. Then we'll talk about internal consistency, and then some of the other things that we can do. Two appraisers, more than two categories, still nominal, right? We can still put them into different categories. There's no order to the categories. We'll talk about how you test for the significance of Kappa. And then we'll talk about validity analysis, what you do if you have more than two appraisers, how you deal with long-term control of discrete gauges, and then also assess capability. So it'll probably take us this time and then our next lecture to go through this appropriately. It'll be fun. Okay. So let's talk about some different examples of when we might use discrete gauge. What is a discrete gauge? And so you could have some different situations. You're measuring something, right? And, of course, I love continuous gauges because they make my life really super happy, and I like variables data because it's easier for me to understand and easier for me to deal with, given that I spent most of my training as a mechanical engineer learning those types of techniques and mathematics and calculus, and we never dealt with nominal or ordinal data. Are you kidding me? They're like, no, we're going to measure flow and heat transfer and fun stuff like that, right? But there are other things you can measure, and sometimes when we measure things, we have to create the measurement system ourselves. And so the measurement system might be something like a survey. Ooh, a survey. You're like, what do we do with that? So, for example, you might, and of course you guys are all familiar with surveys. I'm sure you get surveys for any types of services that you have. You're going to get a survey here for the faculty course questionnaire. So you get to evaluate the course, you get to evaluate me, and so there'll be a scale. You get to rate me on a scale from 1 to 6. They don't let you give me a 0. Sorry about that. But you'll rate on a scale, and so that's supposed to be a measurement of performance, right? Of course, we can do pass-fail, whether something passes or fails, and then there's different nominal variables, meaning different categories that we put things into. One thing, did I tell you I worked for Cargill as an intern? So I worked in a soybean oil refinery as an intern, and we would have to rate different types of oil. Now, beer tasting is it's very similar to this. So you'd be like, oh, that has a nutty flavor, and it's all really sophisticated, and you have mahogany furniture in a tasting room looking over the mountains, and it's great. Okay, oil tasting is totally opposite. You're in a dirty plant, and there's like smoke. Have you ever seen that big cloud? You watch Charlie Brown, and there's like that big cloud following Pigpen around. That's what it's like to work at the soybean plant. Okay, there's just like dirt and soybean oil, like this weird kind of strange oily mist in the air. It's bizarre. Better than the corn plant, but still pretty strange. So you'd be like in this really dark room with, old phone books and weird stuff, tasting oil. And then you'd have to put it into categories like rancid. And then they'd have a trash can right next to you in case you got sick. I know, I just had to share that. But those are different types of nominal categories. You'd be like, ooh, this is a nutty flavor. You're like, whoa, I'm going to just step out of the room here because I think all my teeth just fell out. Yes?
Why did they put you in a dark room with what's going on?
I think we did it in the break room, and that just happened to be the best place to go ahead and do this type of. I know it was kind of old school manufacturing.
I'm shady.
It was a little parts of the operation were a little shady. I'd have to say that. Some of it was fantastic, and other parts I'm like, what is going on in this place? I just don't even understand. Sometimes you'll have a gauge that has low resolution in it. And if you remember, you want to be able to split up the between the lower spec limit and the upper spec limit. You want to be able to split this up into 10 parts. If you have 5 groups, if you can only split it up in like 5 groups or less, you just go ahead and consider that to be ordinal. So if you have low, that's the standard, 5 groups or less. We just go ahead and make a continuous gauge ordinal. So those are some examples of what we would consider to be a discrete gauge. Now, even with these discrete gauges, and even if we're using some type of rating or ranking system associated with our survey, which is our measurement system, there's some parallels between these. And if you did take the CQA part with Dr. Luftig, you probably are familiar with some of these terms, or it might be a little out of date for you too, and that's okay because we'll go over them here. But if you remember, when we were talking about continuous data, do you remember precision when we looked at the target example? And precision had to do with a tight grouping. Do you remember that? So lower variability, precision. The term that's related to that is reliability. And actually, there's 4 different types of reliability that you can look at. We're just going to do a couple in here. Okay, but reliability has to do with there's probably, when you're measuring something, you've got the true value and you've got some error associated, and that ends up being your reliability. So this term right here has to do with dispersion. Okay, there's going to be some dispersion. And so when we're looking at reliability, just like we have measurement error is related to precision, we have a couple things in here, and they have to do with measurement error. Here is agreement. That's what we're looking at. So when we're talking about agreement, there's two parts of this. 1, 2, 1, 2. Okay, repeatability. And who remembers what repeatability is related to when we're looking at a continuous measurement system? Or give me an example in your own words.
Able to repeat the data similarly.
Yes, perfect. Okay, so let's say Lavi has some stuff that she's looking at. Maybe she's looking at, maybe she's evaluating something for good or bad. And maybe she has 10 items that she's looking at. And she says, the first time she looks at them, she says, all right, items 1 through 5 are good, and items 6 through 10 are bad. And then I mix everything up, randomize it, and give it back to her. We would hope that she gives the same results, right? But 1 through 5 are still good, and 6 through 10 are still bad. That would be an indication that she had perfect internal consistency. Now, if she had some of those mixed up, she said, all right, 1 through 4 are good, and 5 through 10 are bad this time. We have some disagreement from her first measurement to her second measurement. And maybe she did a third one after that too. And so whatever's different in there is going to be measurement error or lack of agreement with herself. Can you imagine not agreeing with yourself? Now, I guarantee you haven't. How many of you have taken the Myers-Briggs test more than once? Did you agree perfectly each time you took the test? Did your personality change? Of course it did. Take it when you're like 20 years old and then take it when you're 40 years old. We're totally different. Okay, but, so that may be because you changed, but it also could be the related to the reliability of the assessment itself, the questions that are asked. They're not asked in a way that you're going to use it the same way the next time. Could be not reliable. So, okay, so repeatability, we got that down? So we call that internal consistency. Are you consistent with yourself? Then the next part of this is called concordance. And so, and those of you who took 5620, and that would be you. I thought you took 5620, Josh, but you haven't. Okay, not yet. So with 5620, we had measures of correlation and association. I believe there was a measure of concordance in there. And concordance really has to do with, it's another part of agreement, but this is the within component, and this is the between component. So if I have 10 items, I want to see if there's agreement between Lavi and Afton. So I give them the 10 items. Do they rank 1 through 5 as good, both the same, and 6 through 10 as bad? Or do they have some disagreement in there? What is the level of their agreement or concordance in there? So I can measure concordance not only between gauges or people, if they're the gauge, but also between a standard. Would you want to, because Afton and Lavi could agree together, but what if they were totally disagreed with the standard? And the standard was correct. Problem city, okay? Call the mayor. So, so we have to have concordance between people or gauge, right? And between standard. Those are important, okay? And so with this concordance with the standard tells us something about validity, whether or not we're accurate or not. And so that really comes down here to concordance with a standard, importante. Got that? If not, just go back and look at it and just let it sink in a little bit. But within variation, between variation, and then we're going to compare to a standard. Now, like I said, measuring agreement is a little bit more challenging than measuring disagreement. And disagreement, and do you guys remember McNemar's test for change? You don't remember McNemar's test for change? 5005? You're like, no. You're like, do you remember? I remember there was this test, and there were these cells, and we looked at the B and C cells. Remember that? To see if those changed. They were where people disagreed on something. Okay, it's okay that you don't remember. I'm messing with you. So McNemar test of change, that's how we measure disagreement. We'll talk about that in a little bit. So let me give you an example here. Let's say you have a screen process printed circuit boards are randomly sampled off the end of a production line and visually inspected for defects. So if they're visually inspected, let's say we're using people. Who's the gauge? People. People are the gauge. Visual inspection, people are the gauge. Their eyes are the gauge. They look at it and say, that's a good one. And then they look at it, that's a bad one. All right, so hopefully there's some standard to which they are calibrated, right? So they assess each board as okay or defective as compared to a given set of photographs, which, believe it or not, is challenging to do, especially if you only have like one photograph for the desired state. So, of course, and this happens with visual inspection a lot, there's internal issues related to the assessment as well as return shipment from an angry customer due to nonconformance. And so the statistical facilitator says, hey, maybe there's some problem with the measurement process here, and we should take a look at some differences between the inspectors. And these names were picked, Harold and Eddie. Now, I did not pick the names. We could call these any names that you wanted to. But I believe Dr. Luftig in this original example picked consultant names because I noticed some people in their name, Mike and Peg. I'm like, oh yeah, Peg Wilson. I remember her. She was my original SPC trainer. Okay, so we're trying to determine if there's a sufficient degree of agreement because agreement is related to reliability. We want to see if people agree. We want to see if they agree with themselves and agree between people. So we want to see if there's agreement between the inspectors. So the facilitator randomly selects 100 boards and arranges the boards in a blind box, okay, so that they just grab it. They don't know what it is. And they rate the board using the current measurement scale according to the SOP. And then they record the results. And then here is the question that the statistical facilitator has. How do I perform an analysis to test the assumption that the inspectors are performing in a concordant fashion? Do they agree with each other? Okay, and so we're going to assume for the moment that they agree with themselves between one set of measurements and the next set of measurements. Of course, we would always test that. We would never assume that. Right? We're assuming it for this case. So here's the gauge study results. You ready? Eddie found 40% of the radios to be okay. Harold found 46% of the radios to be okay. They both agreed that 30% of the radios were okay. They both agreed that 47% of the radios were not okay. They agreed on 80% of the radios, and on 20% they disagreed. And so we're saying, assigning a 1 equal to pass and 2 equal to fail. And the question is, how well did they agree? Now, what kind of test could you do at this point? We're dealing with proportions. Okay, well, that's descriptive, right? That's descriptive, but we have to do some type of test, right? Now, here's a couple of ideas. We could test to see if the proportion passed by Harold seemed the same as the proportion passed by Eddie. So I do this test. This is a proportion test, because you remember here we had 54%. I'm not sure where they're getting all of this information. Oh, this is the marginals. Okay. So we're looking at marginal data here, and I'll explain what that actually means. But they're looking at, okay, this is the proportion passed by both Eddie and Harold. So here's Eddie, here's Harold, and what do I see for my test for significance? Are they different?
Yeah, not different.
They're not, yes, they're not different, right? Because so our null hypothesis is that proportion 1 is equal to proportion 2. I failed to reject, so they're not different. But the problem is that this, it tells me this. It tells me this, that the proportion passed by Harold is not different than the proportion passed by Eddie. That's what it tells us. But the question is, what does it not tell us?
It is not telling us within the samples, like for example, if they're doing the defective rate thing for the same sample, it is not telling the proportions, it is telling the overall how many can be.
Exactly. So did Harold pass the same ones that Eddie passed? We don't know. We just know, the ones they passed could have been different samples completely. So we really don't know. This is proportion. The other problem with this is that this type of test is for independent measures. So they're measuring the same items, so there's automatically a dependency created there because they're measuring the same items. And so we can't actually use this test anyway. So I just throw that out there, okay? So equivalent proportions, it doesn't necessarily equal agreement. It's just equivalent proportions. But which proportions are they? We don't know. So that's not a good one, okay? They're really dependent and could be completely different units. Now, another type of test here is related to the chi-square test. This is a chi-square test of association. And really what we're doing here is seeing if there's any relationships between the row and column variables that might be significant. So it's asking the question, is there a relationship here? And there is a significant difference, but even if you switch up all these numbers, it'll give you the exact same results. It'll tell you there's a relationship, but it doesn't give you the proportion of agreement. So this one doesn't tell us about what we need to know. I'll just go ahead and put that on there. No, it doesn't. Okay, so, because if you switch the numbers around here, look, you get the exact same results. Look at the chi-square, 35.756, the exact same results. So there's a significant difference, but it doesn't tell us whether it's disagreement or agreement. We just know that there's some relationship there. So that's not going to help us, okay? So it tells us there's departure from chance agreement regardless of whether this is a disagreement or agreement. Now, here's another test that we do, and believe it or not, this is the McNemar's test of change, right? And you remember this? We're looking at the B and D cells here, and that's where they disagree. So this doesn't measure agreement, it does measure disagreement. And actually, it doesn't answer a question, no, but still important. Because we're going to use this for our test of internal consistency. Okay, so keep this in mind. If I ask you questions on, I don't know, like a test or something, or like you're in 5043 and I want you to do a measurement system analysis on discrete gauge, you'll want to be testing this, and I'll show you how to go through and actually do that. Okay? So no, it doesn't, but it's still important. This one only looks at disagreement. Sometimes we call this a test of symmetry. So testing for disagreement, I mean, you could put 0 in these two cells. It doesn't tell you anything about agreement. And like I said, you can use this for testing internal consistency. I'm going to put a star by it because you need to know. Okay? You need to know that. All right. Okay. So we can look at absolute and relative agreement. Now, looking at this, we have some different examples here between Eddie and Harold and Edith and Harriet. And you'll see here that we have the exact same numbers for our chi-square test, which is not exactly the right test here. But you could see, and 1 is a pass, right? 2 is a fail. So this first time, Eddie and Harold agreed on 60 items, right? 60 out of 100 is 60% of the time. They agreed 60% of the time on the pass items. What percent of the time did they agree on the fail items? 0. 0% of the time, okay? And so look at the results here. They're exactly the same, 0% of the time. Then I could have this comparison for Edith and Harriet. And for the pass items, they agree on the pass ones, 20% and 20%. And then on the items that are pass, what does Edith say? So Edith and Harriet, so Harriet says, okay, these are pass. Edith says, nope, nothing fails. Edith passed everything. Do you see that? Edith's like, everything's a pass. So if you're trying to figure out, okay, which one has better agreement, they didn't agree on any fails. They had agreed 100% of the time on the fails, and we're trying to understand, okay, which pair of these has better agreement? And it really ends up depending on what the marginals turn out to be in the cells. What do they agree on? What do they disagree on? And what is the proportion of agreement they have that's above that due to chance and chance alone? So that's what we're looking at when we're going to look at agreement. Now, if you remember, so there is a probability of chance agreement, right? I mean, if both you and I were assessing something, and let's say just for fun, we were going to use the scale for the FCQ, and let's say Shane and I take the same class, and then we rate the professor, and we both give that professor a 5 in one category. Is there a probability that was due to chance? Sure. I mean, I don't know how Shane is using the scale. I don't know on what criteria he's interpreting the question and what his internal criteria is. I don't know any of that, but there is some proportion of chance agreement out there. And when we're looking at this, you can actually, if you have 2 events that are considered independent, then the joint probability of those 2 events is the product of those 2 events. So you can, if you're looking at chance agreement, we're looking at a nominal category of okay, not okay, right? So like if I'm looking at this example here, I could say the proportion okay in category 1 times the proportion okay proportion okay for rater 1 and the proportion okay for rater 2. Category 2. Well, anyway, this is the chance agreement here. So let's go down and try and just figure out the best way to explain this here. So we have Eddie and Harold. Eddie looks at these items and says, okay, these items are all pass. And so that Eddie says, okay, this is rater 1. Rater 1. This is rater 2. So this is Eddie. This is Harold. Okay. So if I go through and I look at all the items, he looked at all of these items and said, all right, 46 of these are in category 1. That's what goes here. Then Harold says, all right, I think that 40 of these are in category 1. Remember, they were looking at 100 items. We just have it in proportions right here. Okay? I say 40 of these are in proportion, or okay. That goes right here. Then I can look over here and say, all right, what did Eddie say about what wasn't okay? So for Eddie, number 2, he goes down here and says, okay, 54 of those I say were not okay. That goes in here. And then Harold said 60 of these are not okay. And that goes down here. And so if I multiply those together and add the multiplication of those two together, this gives me my proportion of chance agreement. That's the proportion of what could be due to chance based on what we know about statistics, right? Okay. If the difference between the observed proportion and there's also something called an expected proportion is big enough, then it has to be because they are not dependent, or it's not independent, or there's some dependency in some way. And so what we do, what measures that, the statistic we use is something called Kappa. And really this is just a proportion of agreement, overall agreement, minus taking out the chance agreement over 1 minus the chance agreement. So it measures the proportion of agreement that's above that expected due to chance and chance alone. Because you could have agreement with just chance. Let's say we were measuring color somehow. We were looking at Afton and I were like, let's analyze the red on this bag. And she does it visually in a booth, comparing it to a visual standard, and then I use a spectrophotometer. There's still a possibility that we could come to the same conclusion about which ones were good and which ones are bad. Of course, we'd both be asking ourselves, why are we evaluating the red color on a Cheez-It bag? But we would have a fun time eating the Cheez-Its afterwards, right? So if we're looking at the proportion agreement above that expected due to chance and chance alone. So did we determine how far above chance we actually agree on something? So that's what's great about this statistic, okay? We're not taking chance out of it. Yes?
How will we get calculation?
How can we do it? Actually, the software's going to do it for you. Yeah, so you just have to get the information in the appropriate cells in crosstabs. Yep, so you're going to use, this is all in MVP stats, and we are going to use crosstabs to do it. You could do all the calculations by hand, too. I mean, you could do these calculations, right? You would just go through and get your chance agreement, and then I would get my proportion agreement, and I'll show you how to get your proportion agreement, because our total agreement's 80%. But you can just go ahead and let the software do it for you, so you don't have to do that by hand. Okay. So you can see back here, I think it shows, it doesn't show it, Harold and Eddie up here. It doesn't show that. Okay, well they agreed 80% of the time. Do you remember that? They agreed on 80% of the radios. Maybe it was on the second slide here, but we can see it here. 33 and 47 is 80, right? Yep, just checking. Okay, so that's a calculation you could just do by hand, but I would just, to make your life easier, just let the software figure it out. But if you wanted to do it in Excel, that's how you would do it, is you would look at this will be your proportion agreement. Just add those two up. And actually, I did this study on the vision system. When I bought those off for statistical startup, those of you in 5041. And so that I got to send 1,000 lids through for 2 weeks until they could pass the capability study for the gauge. Hey, all I did was stand there and count lids. It was really not hard. They had to do all the fixing. Okay. So this is what the MVP stats output will look like. If you have MVP stats, I'm going to keep my ink annotations here. Show you that. Let me just show you. Have you guys used crosstabs before? Okay, you've used it? Yeah, that's 5005. It is under tests, and you go to crosstabs. I'm going to go ahead and do my columns here. Now you'll see I have rows and columns. I'm going to make this a little bit smaller so we can make it look like we want to. For the rows, I can just put in a name, Harold, and then I can put in Eddie, right? And then all I have to do is just type in the information, 33, 7, 13, 47. Okay. And then once that's, should be able to, I don't know why it's not doing that. Oh, I have to choose something down here and then it'll do the stats for me. Okay, so you can see here I get the, oh, it doesn't want to do that. Let's see if it'll turn. There we go. That's nicer, isn't it? And so all of those calculations, it'll do that for you. You have a proportion agreement, proportion chance agreement. Your kappa ends up being significant. So what that means is there's significant agreement above that due to chance and chance alone. And we'll go through some more specifics here. But that's really just the basics of it. You're trying to say, okay, is there significant agreement? Now, when we assess capability, that still may not be good enough. I mean, maybe we agree 50% of the time, and that's above chance and due to chance and chance alone. Would that still be good enough for assessment of these screen-printed circuit boards? Probably not. Your customer would be like, hey, that's a good one. Especially if we've got Edith involved. She just passes everything. I don't know what's up with that, but trip to, perhaps she can't see the differences. Okay, so we're determining how far above chance we actually agree. And so if we look at this here, this numerator represents true agreement, right? Because we're taking out this part of it due to chance. Oh, sorry, I'm going to make this prettier. True agreement, right? And then we divide that by the possible amount of agreement that they could have above chance and chance alone, right? So there'll be one minus. One would be perfect agreement, right? Okay, so possible agreement. All right, so when we do this test, this actually here, you'll see here, this is a Z value that we use for kappa. I'll give you the calculation here in a minute so you can look at it. And also back here with this 59, we have 59% agreement above what we could have had by chance and chance alone. Agreement above chance agreement. Okay. All right, so we have a Z-score, and we're testing the hypothesis because we have kappa is our statistic that we're looking at, right? And kappa prime, I don't know if they have kappa prime down here, but this is actually what we're testing here. So this is the population parameter. So this would be kind of similar to like we would look at the statistic X bar and compare it to mu, right? So we're testing the hypothesis that the Kappa prime, the population parameter, make sure I write that correctly, equals 0. Okay, so that's saying there's no agreement. That's above and beyond chance. No agreement, above and beyond chance. And sorry I'm taking a slow time with this, but sometimes this stuff kind of takes a minute to sink in. At least it does for me. And I know it did for Dr. Ray. So if it helps you feel any better as you're going through this, you're like, wow, this is interesting. Maybe it's just sinking in for you right away. Dr. Ray, it took him years to master some of this too. So be encouraged. All right, so that's what we're doing. So if we fail to reject, there's no agreement above that beyond chance. It was just chance. So we have some work to do. So if you do reject, though, there are some confidence intervals that we'll have to calculate. And that's challenging, but I actually have a spreadsheet you can use to calculate confidence intervals. We also have them on MVP stats. Okay, so again, this is the statistic that we're using to compare to Kappa prime. And this is the calculation for the standard error when Kappa is equal to 0, no agreement. And so we're testing this with a z-score, basically. All right, so here's some advantages to using this, is that you don't have to have symmetry of marginal proportions. So if you remember, we have our little contingency table here. Remember this was like 33, what was this one again? 47. I forgot what the other ones were. That's 80.
7.
7, and this one was 13?
13.
Okay, 13, and then we had our marginals out here, right? 40, I can't remember what all of these. 60, 54, and
46.
46. So this is what we call the marginals out here. There has to be symmetry of these marginal proportions when you're using the chi-square test for it to be considered to be valid. And so what's nice about Kappa is you don't have to worry about that. It's not one of the underlying assumptions associated with the test. So we don't have to do that. The other thing that's kind of cool, I'm just going to erase this so it's not messy, is that, of course, you have chance agreement accounted for in its calculation. But we also can use this. When you have a contingency table like this, you only have 2 categories that you can use. Kappa can be used for 2 or more judges or inspectors, so you could have something that goes longer than that. Okay, and also you could have more than. You see how our little table's getting better here? I mean, we can do more than just one category too. So let's say I'm judging something and I don't know, soybean oil, and I'm going to make Afton and Shane do it, and Josh, since they're in my 5041 class, and they're tasting those. They could put them into categories like rancid, nutty, and the other one was. Oh gosh, it had something to do with like leftover oily feeling on your tongue. I can't remember the exact name for it, but that one was pretty bad. And so they had standards for these that you'd have to calibrate yourself to, by the way, as well. I don't know why.
I'll stick to beer.
I know, really. It's just like, who wants to taste Wesson? Nobody in here. We'll put it in a cookie, and that's the way it should be. That's about it. Okay, so we can use this for 2 or more judges or 2 or more nominal categories. We do have a way to, if you're looking for ordinality, there's other techniques you use. We do Kendall's, I guess, what is it, Kendall's W, there's Friedman, those are ordinal techniques. We're not going to talk about those. We touch on them briefly in 5620. You do a homework and you move on from that. If you want to get into that, go for it. But you probably have to go over to social science part to learn more about that. We can get an approximate confidence interval, whereas other things we wouldn't be able to do that. So it's useful for us, and that's why we like to use it. Okay, we're measuring the proportion agreement above chance agreement, and that's kind of nice. Now, some notes on Kappa, and after this we'll take a quick break because I know this is a lot to take in. It can vary between -1, which would be a complete disagreement, and +1, which should be complete agreement. Okay, so we could have complete disagreement. We could have agreement, if Kappa's 0, we're kind of in the area of chance agreement, right? And then we have complete agreement. So if you have complete disagreement, would you say something is wrong? Yes, something is wrong. The way that you're judging it, something's going on. So that should be an indicator as well. So we're going from -1, 0, all the way to +1. So this is kind of similar to your Pearson correlation, right? So if you have, if you're looking at variables data and you have a negative correlation between two variables, we call them negatively correlated, right? As one thing goes up, the other one goes down. Kind of similar to that. So if your Kappa ends up being less than 0, the level of agreement was below that expected by chance, which is telling as well. And then we'll talk about Kappa max coming up here soon, because that can help us figure out what's going on wrong with how we're either using the scale or assessing items. But there is actually a maximum value of Kappa, and it's a function of symmetry of the table and how people rated things. And we'll talk about that when we come back from our break. Okay, 6:36 right now. Come back at 6:46. We'll continue our discussion on agreement.
I'm not coming back.
You're not coming back. I'm not talking about that. It is pretty interesting. Explaining that 50-40, what we're talking about survey interview questions. So they're polling somebody. If you don't ask the right question, it's going to give you talk about reliability and validity of the survey questions. And then you want to ask the question that's going to reveal what gives you some type of predictability. So apparently, whatever questions they asked in polling for these people who did the predictions for the election were the right questions. Interesting, huh? I know. So I'm interested in that aspect. Other than that, I'm just like,
SQA quiz yet?
Mm-hmm.
Is it long?
No. All I've done so far, so I think there's like 22 questions, and 5 or 6 of them have like a part B and or C. And I just went through and answered what I could without even like going back through all my notes and stuff. And I probably answered all but like 8 like blanks, or 8 or 10 blanks. So that's all I've done so far, but some of them were like, I'm going to need to look this up again.
I just opened it. Is it all like just kind of
Yeah, it's pretty much
conceptual?
all fill in the blank stuff, except for like those ones right there, the 4 through 7, where it's like, is this, or this?
Okay.
But yeah, for the most part, it's all just like
Sweet.
stuff we've discussed in class. The things that I like, I'm gonna have to go back and look up were the ones somewhere toward the end that are like, what was the specific, very unique aspect of this one case study that we talked about?
Oh.
And I was like, I have no idea.
Yeah, I haven't even had a chance to like look at it at all. Class,
What final?
like presentation.
Oh, the presentation. Sure, kind of. I've thought about it a lot and gathered very minor information. That's gonna be brutal.
Just didn't know if I was the only one on that boat. I signed myself up for so much, and I've been trying to get financial data for my company for like a month, and it's like so hard to get.
That's so frustrating.
And so it's really hard for me to do anything, and so I'm gonna have to just like make a lot of assumptions because the only time I can work on it is next week.
That's no fun.
Yeah.
You guys talk about project?
Yeah.
Yeah.
So I have a group project. It's quite complicated. I think
That's
working by
why-
yourself is easier.
Yeah, probably.
Mine is,
Yeah.
I don't know. Too busy about this semester.
She was pretty thrilled with my proposal, and I kind of just threw that together. So
Same.
the rating of the presentation is equal.
Yeah.
I don't know how much else she wants me to do with that either. If I'm gonna do like a presentation, is she expecting me to like send her copies of all of my analysis and stuff, or what? But we'll see.
I don't know. I mean, I'd set it up like I would for any presentation at work, and I would do like your main however many slides, and then just have a bunch of backup slides that you don't go through, but like she can just
Look at.
look at her leisure.
Good idea.
Hey, after. So after you took the 5620, you think you can apply that to your job?
Hey Mario, where are you from?
Why do you ask?
It's
Not
quite,
right now.
it's quite complicated.
So
Right.
I don't think so.
anywhere else.
Yeah, when we were talking about how hot it was in here.
Yeah, I could.
Remember dry versus
because
humid?
of the nature of my work, we do
Somewhere, was it Alabama?
unique
Oh,
things
it's
that we do
Alabama.
on
Yeah?
this.
Did you go to school there
So
or
it's
somewhere in
really
Alabama?
hard
I did.
to
University of
gather a
Alabama?
lot of data
I did.
for any
Big.
of that.
Kind of sports teams or not really?
I don't like football.
No?
I gotcha. So, and you
Right
work
now,
in like a
always doing good, man.
quality field or something
That's
like
not
that?
fair.
Not
So I work in aerospace and we build
Uh-huh.
satellites.
Sports do you follow?
So, and
Watch
your
any
job
sports,
in
man.
like a specific, you work like a research,
I watch the UFC.
something like that.
I guess that's
So I work
That's a
on
good
the
one,
strategic
especially right
side,
now.
and
Oh.
operations.
This-
I
so,
gotcha.
basically make sure that we, at a very high level, are able to build satellites. So when we're bidding on new stuff, depending on what the requirements are, if we can handle that based on what we're already doing, how many clean rooms we have, and all like the test equipment we have, and just strategically planning all of that. And yeah, because it's so difficult because every satellite we build is so different that it's really hard to. It's like comparing apples to oranges with every single thing we do. So it's kind of hard to use any of that knowledge. I feel like I'm going to use a lot more of like stuff for work. If I went somewhere else, I could use more of the data.
I think maybe consulting company,
Yeah.
but I cannot remember everything
I
that he
impressed
teach
my
though.
boss thanks to you today, Wendy.
It's
Thanks for that.
complicated.
Yeah.
I just want to know
Yeah,
like what
so
scenario I have and
Currently
then just
taking
apply
over
for it.
our
I'm
printing
okay with
service.
that. But if
And,
if let me
so
speak like
I
him,
run the walk-in centers, and
Yeah.
I'm going to be in charge of our printing service.
can you do that? You feel confident enough to do that?
I think I could with some time. Like, I think
We don't
a
like
lot of this stuff.
budget for it. We pay Xerox.
I've learned the concepts and I've learned the tools, and so I know I can if I recognize
paper,
like a
ink, toner,
certain
yada, yada.
issue,
And then
I
at the end
know
of the year,
what to go look up, like go back and look up, and I can
okay,
kind
how
of
much
get
is
my
that?
way through it.
I like his homework. Yeah, it's a lot. It's like it's real.
Yeah.
I like that.
Yeah.
And beyond that,
Taking over printing
I
is my
don't
boss
know.
and I
I'm
are
not
going
sure.
to kind of like dive in.
I think maybe I'm taking 3 classes
get
and
all the
I
details
don't
of
have time
why
to
it's
review
costing
in
us so much and
details.
how we
Yeah.
I think I need more time to do that.
and then that
Yeah, I
turned
mean, I think
into
it's one of those
discussing
things, like, unless
hopefully if we
you
save
use it
all that
all
money in
the
printing,
That's-
leadership will let us use that money towards building up the
Oh,
Welcome
really?
Center service.
Yeah.
Exactly.
It's like-
Same.
So,
don't
yeah, that's why
spare
it's so
money to
good
do
at
anything
this.
that we want to do to give good services to the
I
students.
got you.
Whereas
And then we started
my
talking
job,
about
a lot of the stuff I do
the
does
amount of
involve
money
the
we
BP,
pay, or like the budget we have to pay
high
our
level
student
management
workers
side of it, so
versus
I
how much time they're working and not
a
working
lot
when
better
they're
at
sitting
that
there.
than just the
What my project is
part of it. And I can definitely stumble my way through, but it takes
in like 3 weeks I'll
a
have
lot
the
longer.
whole
And
analysis for you.
because now I haven't done it for
I know,
Just saying.
but
8 months or
it's a
whatever.
benefit of
Definitely have to like dust it off to use it kind of thing, but
Right.
I'll be sure to
I don't know. I
put
think
that in the fine print on
it's
my
really good
presentation.
to know
You get point,
plays and like what you can do with it. And I think as long as you save all the steps, you can kind of stumble through later on. But you should definitely
Well-
try to do something like a
Yeah.
consulting type. You want to use it like right off the bat, or
Right.
like work with
I
a
want
company
to,
that, like,
but
produces a lot of stuff. Would be helpful.
That's great.
I know. I'm not sure about myself though,
Yeah.
About what?
about these things.
Yeah. Do you know what you are kind of interested in at all, or
Yeah, I am. So into, yeah.
into it? Do you know what kind
Quality, I think, yeah. But not like a Dr. Ray. He's intelligent.
He's got years on you.
He has a lot of years on you. 71. Still going strong, eating Cheetos and drinking Pepsi. Okay, we're going to go ahead and get started here. I guess I could wait one. Well, I don't want to. I want to go ahead and get started because we've got a lot to cover. All right, so here are some other Kappa-related statistics. Now, you may be wondering, hey, you just gave me Kappa, okay? Kappa is the measure of the proportion of agreement above that due to chance and chance alone. Why are you going to throw these other things at me? The reason why we are going to look at these other things is because let's say you don't have great agreement. Let's say you agreed 80% of the time. It was significant. And now you're like, well, that's not good enough because really I'm not capable. This is not a capable system, capable gauge system that I have here. And I want to, not take up a lot of my, I don't want to have measurement error. Whether that's due to some problems with internal consistency from person to person or it's between people. I don't want to have that type of error. I want to know what the truth is. I need to know the truth, right? That's what I'm trying to get to. And so I don't want anything to be masked by measurement error, whether that's a continuous gauge or a discrete gauge. So what I can do, I'm going to calculate some of these statistics here because what that does is help me figure out where I'm missing it. And we can compare some of these things that give me an idea, okay, in which area should I focus in order to make improvement to my discrete gauge system? Now, when we calculated our P to T ratio, we did the percent measurement error due to repeatability and reproducibility, and so we had some idea. Similar type of thing here but it really will have to do with how are we using the scale and how are we assessing items. There could be differences between that. And so we might have to make some clarifications on what the scale really means, or we might have to make some clarifications on how you assess items. It all comes back to training. Both ways comes back to training, but what area you focus in might be different. Okay, so the first statistic here that we are going to take a look at is this statistic called proportion of observed maximum, aka POM. Okay, we'll just call it POM. It's easier that way, right? And so this is the POM is going to be what they could, the maximum amount of agreement they could have. Whatever the minimum is of the proportion of agreement given these marginal cells. So really, if we look at this, it's based on the minimum values. So let's take a look at, we're looking at Harold and Eddie. And so if I look at the category within row 1 here, Eddie said 46% of these are good, right? But Harold said 40% of these are good. So really, if they were going to agree on stuff, the max they could agree on is 40 of them. So you're kind of limited by whatever the lowest one is. Now, of course, I could look at what they disagreed on, too. Harold said 60 of these are bad. Eddie said 54 of these are bad. But those numbers are higher. So it's going to be the minimum proportion of agreement, depending whatever that one is. So the max they could really agree on is going to be, it's going to be the sum of the minimum for, so it'd be 40 is the minimum there. And for disagreement, it's between 60 and 54. And so 54 is the minimum they have there, and I sum those up. So for like the max agreement they could have, they had 80%, right? The max agreement they could have could have been 94, based on what the marginals came out to be. They could have possibly agreed on 94 of them, either as bad or good. Just let it sink in a little bit. Okay, so we're going to take the sum of the minimums, the proportion, whatever the cell is lowest for the pass, whatever proportion here, and this is for this example, right? A fail, whatever the sum of those proportions is, that's the maximum observed proportion agreement given the marginal constraints. So you can't agree on more than the minimum. It could have happened. It didn't happen, but it could have, right? So Eddie could have agreed on, he could have said, oh yeah, those are the max that could have happened. He could have said, yep, 40 of them are good. Now, I'm not saying that this is the right assessment. I'm just saying this is the maximum amount of agreement that could happen. But if Eddie said, yep, the 7 that he said were fail, if he said they were pass, the max agreement that could have happened was 40 on that. And then if we look at the 2s here, it looks like if Harold would have said, he said that this percentage here, he said 13 of them. Eddie looked at 54 and said they were bad. The max agreement that could have happened based on what he limited to be could have been 54. And it's just a function of what it turns out to be based on what their assessment actually is. Not what it should have been, but it's just what could have been given what we call the marginal constraints of how it turned out. I'm just going to put, given marginal constraints, how it turned out. Okay, So what we can do is say, all right, if that was the maximum they could have agreed on, we put this value in here. Remember, kappa is the proportion of actual agreement minus chance agreement over 1 minus chance agreement. Well, a kappa max, what the maximum kappa could have been, maximum kappa statistic could have been, is instead of putting the actual proportion of agreement, we put the maximum it could have been, given the marginal constraints in. And so this is the best we could have done, given the observed lack of symmetry of how everything turned out to be. Okay, so they put them in these different categories. Sometimes, they said this is bad, this is good, this is bad, this is good. There's some constraints based on how they judged things and how it turned out. So we use that to our advantages. To our advantage, because when we're disagreeing about something, there's two sources of disagreement. One has to do with differences in how the scale is being used, or they're using different scales. That's a possibility. It's usually different in the use of the scale. And there's disagreement as to whether a given item is either good or bad. So again, I'm going to use a scale here. Here's your performance review. You ready? Doesn't meet expectations. Met expectations. Exceeded expectations. I abhor the scale. Here's why. Okay, let's say I have this scale, and let's say that Josh is the employee, Lavi, you're the employer, and you're going to rate Josh for his work performance. And Josh, you think is amazing, and you expect him to do work 60 hours a week and bring in $1 million worth of revenue for the company. And he is a star performer, and that's what you expected. So you rate him as met expectations, right? Now I come in and I expect him to have different performance. I expected him to, show up on work on time, have, bring in a significant amount of revenue that's less than $1 million, and work 40 hours per week. That was my expectation, and so I give him, he did more than that, so I give him exceeded expectations. So I used the scale differently than you did. Well, that I told you did, right? We use the scale differently, which is why this kind of drives me crazy. Because what if my expectation, for performance review, what if my expectation is, yep, I expected him to suck, and he did. Met expectations. Really, it's not a good scale, right? So there's different ways that it can be interpreted, and that could be problematic. Now, there could be disagreement also on whether the item is good or bad. You're using the scale the same way, but maybe I have a scale, whether I say it's good or bad has nothing to do with the scale, but really my own assessment of it. Yes?
I think that is a drawback for this assessment because, as you said, if we have different level of perception and still, suppose if we still rate Josh met expectations, we agreed, but the underlying perception might be completely different, and in future assessments, that we might branch out. And we might not yield the same results. In that case, will this be the...
Well, that's an example of a bad scale because there's too much room left open to interpretation on what meet expectations means or doesn't meet or exceeds. So you have to, that's where you have to really be clear on what is what associated with the scale that you're using. There has to be clear definition. And see what happens is, it's called boundary fuzziness. Like you can't, what's the difference between doesn't meet and meet? If you're using the FCQ, What's the difference between a 5 or a 6? You know, it's like the dean, when the dean evaluates this, he thinks a 4 is failing. He thinks a 4 is an F. But you might think a 4 is, it's pretty good, 4. You know, or, it's okay, meh. 4 is a meh. You know, the dean's like, 4 is awful. So, I mean, it really has to do with how you interpret the use of this particular type of scale. So if you're using this, you've got to be really clear on what, you know, if you're doing 1 to 6, what a 1 means, what a 2 means, what a 3 means, what a 4, 5, 6. Now, that's not going to change for the FCQ, but for you, when you're using something like this, some type of scale, you have to be clear, as clear as you possibly can on what's good or bad. You know, it's easier when you get kind of, if it's an actual gauge itself, on whether it's going to say it's good or bad, it's a little bit easier if it's doing some type of measurement, and then it's not genuinely dichotomous, it's artificially dichotomous. So the example of that vision system, we had a grayscale type of system that it would measure, you know, it would measure color coming back and say it's good or bad based on some standard that we put in there. So the boundaries were a little bit more clear. They could be tweaked, but there's less, when you're dealing with humans, it's a little more challenging. So what we do with this here, because we have 2 potential sources for disagreement, is we figure out, okay, here's kappa max, what the maximum could be. It's a maximum value you can attain if only disagreement is that found by the lack of symmetry. Okay, so this is only related to lack of symmetry, which has to do where everything shows up here in the marginals, which is related to what ended up being assessed differently, right? So this is related specifically to differential scale use. So it's an indicator that people are using this scale differently. And so that's where you can use this to your advantage to be like, okay, now what do I work on? What am I going to have to make more clear so that I can get my inspectors or assessors to have better agreement? And it usually comes down to clarity. Now, when it comes down to item assessment, you're going to have to do training. So scale would be related more to clarity. Item assessment would be related more to training. And sometimes training can be hard, especially if it's a visual assessment. And if you've been to Method 9 training for air emissions, nobody's been to smoke school? Okay, well, they actually have this training, so if you, I won't talk too long about it, but I'm not even going to talk about it. It's going to drive you crazy. You have to assess a plume of smoke coming out of a stack as to what the opacity is and if it's okay or not, and then submit that information to the EPA as part of a Title V permit. So if any of you are going to be the environmental engineer in your plant, you'll have to go to smoke school and be recalibrated every 6 months. But don't worry, the guy who does the training teaches you to cheat. So no problem there, right? Okay. So differential scale use, if we had perfect symmetry, everything turned out to be perfect, that means we'd have nothing in those B and C cells, right? We'd have perfect agreement. And statistical assessment of symmetry, of course, is going to be done using McNemar's test. And again, this lack of symmetry has to do with differential application of the scale or boundary fuzziness. What's the difference between a 1 and a 2, or a 2 and a 3, or 3 and a 4, right? Or what's the difference between okay and not okay? I mean, it could be open to interpretation, and especially when you get into visual assessment, it becomes challenging. Okay. So Kappa max also, if you want to do an easy assessment of this, you could just do 1 minus the proportional difference found in the off-diagonal cells. So if I take 0.13 minus 0.07, that's what, 0.06? 1 minus 0.06 equals 0.94, which is this plus this. Okay, your Kappa, Kappa max. But anyway, that's your max proportion, and then we would put that in. Sorry, that's not the exact right answer, but that's the number that we would put in here. That's 0.94. All right, so when the disagreements involve only one row or column, then it will, the Kappa max and Kappa will be equal. And I'm actually going to, would you guys like to do a binary for extra credit?
Of course.
I thought you might. I'll give you a binary to do. Over the break. You'll have to take you like 15 minutes. And it'll help make this whole part a little more clear on how things change when the proportions in each cell change. And you'll look at Kappa, Kappa max, and your proportion observed maximum, POM. It's just putting in numbers. Really. That's it. Okay? We'll do that. It'll help you understand how things change. Okay, so 1 minus Kappa is your loss in agreement due to disagreements associated with differential scale and item classification. So it has those two sources of disagreement here. Two sources of disagreement. 1 minus Kappa max is a loss of agreement above chance due to non-symmetry, and that's just your things that involve scale usage. And if you look at Kappa max minus Kappa, that's due to disagreements on items, not differential scale use. So that's how I can figure out. I do those calculations, see what the biggest differences are, and then I can figure out where I'd want to work. You could even put it into a bar chart. No pie charts, but you may put it into a bar chart. You're not allowed to use pie charts. Okay, so this is what. I know this looks kind of interesting here, but this actually will give you an idea of where you should focus here. So we have all of these numbers in here. This is our proportion due to chance, proportion agreement due to chance. And here's our proportion agreement due to skill, but these are the losses here. We only arrive at this because we're calculating what these different losses are, and we get that information from Kappa and Kappa max, which is on this page right here. Okay, oops, so let me go back here. Okay, so there's our Kappa numerator. So if we figure out what the proportion observed minus the proportion due to chance, that gives us, our proportion that above chance that was due to actual skill between the two assessors in assessing, okay, skill that led to agreement. And then this is what it could have been. This is related to items, and this part is related to scale usage. So if we're doing a final assessment of why we weren't capable, this is where you really can get into what I should do. To get better agreement. Don't worry, we're going to look at some examples. We're just getting some concepts down here. All right, so this is just another way that you could look at it here. So disagreements would be kind of like this. Let's say we're looking at a beer bottle because why not? Because why not, all right? So this person looks at the beer bottle using the scale and says pass. This one rates it exactly the same way and says fail. This is just like of course they wouldn't give actual numbers like this. This is representing some type of thought process that's going on. See the thought bubble? This is their thought process. And this is related to how they're using the scale and found whatever the scale happens to be, pass, fail. Let's say they're looking at a beer label bottle, a beer label, and how well it adheres to the beer itself, the beer bottle itself. Well, this person uses the scale and says it's a pass. This person uses the scale and says it's a fail. It's the same scale, right? But they're using it differently. Now, another type of test we used to do, here's a beer can, because I know you guys wanted a beer can example. So this part up here, if you put a label on the can, this part up at the top, get rid of that. This part stayed silver because there was a lid that was going to go on it anyway. There's no reason to paint the top of the can when it's going to curl over at some point and be like, here's the can. There's going to be a lid that goes on top of that and cover it up, right? And so we'd have to set label height. And we had a little gauge that would fit over the top of this, and if you could see silver sticking out, it was a go, no-go gauge. But here's the thing. What if you put that on and there was just a little piece of silver there? Some people would say that's okay. Others would say it's not okay. Same scale, but different use. Make sense? Okay, good. All right, fail. Now, let's take a look at these folks. They're looking at the beer bottle here now, too. Okay, now this is looking at the same beer bottle, and we're saying, okay. If I switch some slides around here, so sorry about this. I don't know what I just did here. Sorry, I wrote my notes and then I mixed them up. Give me just a second to reorganize this. I wrote it down so I wouldn't mess it up. So now, let's say one person says this is an 18, and the other says a 19 and fails it. So this would be like, I have these two items again. Here's my silver part. Okay, one person, we put the lid over, and it's just like this. Same scale. Now, this is not a good example. So this is looking at it and saying, yep, this is a 18. Let's say we're looking at the color red, how red the label is. And I'm looking at this and I'm saying, okay, 20 is dark. And the scale goes from 15 to 20. 15 is light. And I evaluate this and I say, yep, this item is an 18. It's a pass. And this person says, yep, this item is a 19 and it's a fail. So the item was assessed differently as opposed to scale differences. Good example? Or do you have a better one?
Can you have another one?
Well, I could. I'm thinking of one that's probably... What's that?
A can?
No, it's not a can. I got to get this one out of my head. It's not appropriate. What's that?
At a restaurant.
Yeah, we could take, let's say we're tasting chocolate cake. I really use some chocolate cake right now, and so could you. Flourless for whoever's gluten-free. You taste the cake and you say, oh yeah, okay, let's say a 15 is bad, 20 is good. You taste it. Lavi's like, yeah, that's an 18. Pretty solid 18. Afton, she hasn't eaten all day. She tastes it. She's like, this is a 19. This is in the top 10 of cakes I've ever tasted.
Probably say that for every cake.
Well, I pretty much say that for every cake, too. I mean, I don't think I've ever spit out a piece of cake in my life. Can't say the same for other items, but definitely not cake. Okay, so we're using a scale the same way, good to bad. It's just the item we assess differently. So pass. This person says fail. Horrible chocolate cake. Okay, so if we say that the agreement is above chance agreement, then of course we can calculate a confidence interval. This is the calculation. And of course you could do this by hand, or you could just let the software do it, which is nice, would be nice. So this is the standard error used for Kappa when Kappa is not equal to 0. And so it's a little kind of a hairy type of calculation. Yeah, that's pretty hairy. So let the software do it for you. Okay. So next part here is how we do these procedures. So that was really just the introduction, the conceptual types of things. We'll do some work here. I'll give you a binary to do, which will be related to calculating Kappa, Kappa max, and the POM value. And then we'll use it. We'll go from there. Okay. We'll use it at the beginning of class to help us solidify this stuff in our heads. So next here we have measurement system analysis on discrete data and how you would actually do one of these studies. So keep in mind here that our sample sizes for these types of studies tend to be large because when you're dealing with discrete data, your sample sizes are always going to be larger anyway, just because of the nature of the data. It's hard to extract information out of discrete data because it doesn't give us as much as variables data. So we have to do more. Our sample sizes are always going to be larger based on the underlying distribution. So sample sizes tend to be large, meaning that they're usually greater than 100. 100 would be the minimum that you would want to have. Like I said, when I did the BIOF studies for the vision system, I used a sample size of 1,000. Because your agreement indices may not be accurate if you have a sample size less than 30, and your confidence intervals should definitely not be calculated if your sample size is less than 100. So 100 is your minimum that you'd want to do. I recommend, if you can, you want to have more assessments in this. Now, if it's a visual assessment, that's not necessarily going to be popular. I was talking with Dr. Ray today. We were measuring can shininess. And just to make things easier, we said, all right, because we had to, we had a scale of 1 to 5, and so this poor young lady, she had her PhD, she just got her PhD, and she had to sit in our can plant and assess can shininess, for maybe a week. I mean, thousands and thousands of samples, and she had to keep recalibrating herself. And Dr. Ray developed this experiment, and I went down there and said, hey, you remember when you made Lisa deal? I go, that's probably why she quit after a year and a half. So it's not easy, but useful still. Okay, so when you do this type of study, you'll see this thing here. As process improvements happen, the sample size tends to go up, and really it has to do with a proportion defective you'd want to find. So ideally, if you're doing some type of vision system assessment, let's say, if you're looking for good, bad type of stuff, okay, not okay, you'd want it to be similar to whatever the proportion is in your population. So if you have a lower proportion of defectives that you're looking for, you'd want it to be similar. Typically. So if your proportion defective is 5% and I had 1,000, I would take 50 of those and make them bad when I'm doing throw them in there for the assessment, and then the rest of them are going to be good. Now, next semester, if you take 50-40, who's taking 50-43 with me next semester? Afton, Lavi, Josh?
Doing 5,900, so.
Okay, 5,900. Okay, that's good. That's good. You'll be fine. When we do our measurement study, you'll want to do a 50% defect rate. I'll just go ahead and tell you right now because you won't pick up the differences. I'll tell you again next semester. I don't expect you to remember that. But when you're doing this kind of study, so when I did this, gosh, I think when I had those 1,000 lids, I think I had 3 in there that were bad. Because that was typical of what they would see for proportion defective. So they had to pick out the 3 bad. The machine had to pick out the 3 bad ones. And after 2 weeks of tweaking, we finally got it to be able to do that. A potential study. So we're doing the same type of stuff with this gauge. We've got all these different measurements, or when we're looking at the different gauges, but we want to see if a gauge or assessor or inspector, if they have the potential to be capable in a short period of time, and then we'll look at stability through time. And most folks don't have the wherewithal to do this. You get through this, and people are like, yep, we're good. Ongoing, though, if you had some type of assessment, you'd probably want to make sure that your gauges were stable through time. I mean, let's say Josh is great one day, but maybe through time, he's all over the map. You don't know. If you're using him as a gauge, using Lavi as a gauge, then you want to make sure they're consistent through time, or you're going to end up with somebody who puts a blue Budweiser can on a mug root beer pallet because they can't see. Just saying. Okay, this could be, like Lavi said, a subjective analysis if you're not clear about this. So in order to even have hope of getting agreement, the first thing you have to do is have a standard operating procedure. So this is critical. Okay, and so in the standard operating procedure, it should be clear on what the boundaries are for the scale, whether, okay, this is a good one, this is a bad one, or if it's, you're rating it 1 through 5, here's how they go into the different categories. Or let's just say you have good, marginal, and bad. Make sure that the boundaries are clear. Otherwise, you're going to have some different use of the scales, okay? And then for training purposes, that's where the item assessment comes in too. So you have to train whoever's going to be doing the assessment, if it's a person. If it's a gauge, like the Presco Vision system, we had to train the system. We had to make some changes to the system so it would be. So here's an SOP. Let's take a look here. Compare the intensity of the production part to the intensity displayed by the standard part, and reject the production part if the intensity displayed is significantly off standard. Is that a good SOP? If you read that SOP and then you went out to do that, could you do the job? No! You're like, what's intensity, first of all? What do you mean? Okay, the intensity. And so we're looking at the intensity of the light, right? So, I mean, that's goofy. So you have to make it concise and clear, and then there have to be training on it as well. You can't just put that out there and be like, why didn't you do it right? If they didn't do it right, it's because you're the problem. Sorry, I had to say it. If you're writing the SOP, it's because you're the problem. Got to make it clear. Okay. Assumptions here is that the test or sample units analyzed are independent, and the categories of the nominal scale are independent, mutually exclusive, and exhaustive. And of course, we know that's part of a Bernoulli trial. The judges, inspectors, or raters operate independently. So what that means is they have no knowledge of somebody else's assessment of that unit when we're doing the scale, just like the continuous study. And so we want to make sure we have validity associated with our study. But if I see that Josh rated that one a good one, maybe Lavi would be like, wait a minute. Well, if he said that was good, and I know he's a good operator, I better put down that that's a good one too. She might think that subconsciously, not explicitly, but it might be tacit, and we want to make sure that that is really her assessment, right? So in the case where a single judge is rating the same set of units on a repeated basis, the implication of this assumption is that the first rating of any unit is not known on the second iteration. So again, that's where randomization helps us out. So if you have a group of 10, you would know what unit you're looking at and be able to compare your first measurement to your second measurement. And then also there's no restriction placed on the distribution of the ratings too, if you're using a rating scale. Okay. Next, nominal categories are unordered and equally weighted. So when we're looking at nominal stuff, we're not saying that because we use ordinal techniques if it was not nominal. So an example here that we could see, we could have categories that are okay. We could have a category of scuffed, chipped, too many scratches. One's not more important than another, or there's not an order associated with those. And of course, we could look at this and say, we could say okay or not okay on agreement, and then agreement on reason within not okay. So we could look at this okay versus 1 versus 2, and then when we look at okays, we could see how many were scuffed, how many were chipped, how many were scratches. And then we could look at disagreement within there too. How many were actually scuffed that somebody said were chipped, or how many were chipped that somebody said were scratched, stuff like that. It's possible. And then if they're not equally weighted, you could use a weighted index. I've never done that myself, so that would be in this manual here. If you wanted to read about using a weighted index, I will not require you to do that on the final exam. I'll help you through the final exam, okay, on this one. Because really what I want you to do is learn how to do it, truly. All right, so all measurement systems, of course, are tested under the same conditions. So if I have Shane and Afton, I haven't mentioned Mario, okay, we'll say Shane and Mario measuring, I wouldn't put Mario in the break room, the dark break room with the dirty, torn up phone books, and then Shane would get to go in the mahogany wood tasting room and then do some type of color assessment, right? They'd have to be under the same conditions. Otherwise, you're already messing up the validity of the experiment. Okay, so you may search for an equal number of items in each category. So just remember this for EMEN 5043. It kind of helps us to pick up differences for the scale and item use differences and what's going on with the process. It could cause some external validity problems, though. So this is kind of good if you want to do equal, like 50 bad, 50 good, something like that. But that doesn't really relate back to what's actually happening in your process necessarily. Yes?
Can you please tell me once again about external validity and internal validity?
So, gosh, I have an example of that. You have, here's, this is your target population, right? Sorry. This is your target population. This is your research population. And this is your sample that you take. So your sample that you take should be from your research population, and that's your population that you're able to actually study, what's available to you. And so you want your sample to be actually taken from the research population. That research population should be related back to your target population. So this has to do with external validity, the relationship between the research population and the target population. So if I'm going to take a sample, I want that to be from my research population, right? That's what's available. That has to do with internal validity. External validity is your target population. So if I take a sample, 50 bad, 50 good, from what's available for me to sample, that might be okay for internal validity purposes. But if what I really want to relate this back to how I run my process, so let's say I have that, I have the Presco vision system. Here's the camera, and it's watching lids go by, and the proportion that it's actually going to see is like 3% defective, and I tested it at 50% defective. There's some problems with relating what I did my study to back to what I really wanted to know about, which was in the target population. So you can do that, but that's what I'm saying here is that this might be a good start to do something like that, but ideally you want to test it under the conditions that you're going to be evaluating it for. Make sense? Okay. All right, so repeated assessments are recommended to assess internal consistency. So I want to make sure that Mario and Afton, like Mario measures once and then he measures again. I want to make sure he does it the same each time he does it. I would have to have him do the same thing more than once. And I could do the same thing with Afton, make sure that she's consistent with herself. So that's what we have to do for internal consistency. And the same thing goes here with concordance and validity. Remember, internal consistency has to do within variation. Concordance and validity, which is concordance with a standard, right? Are going to be confounded with internal consistency too. Okay, so if I'm not consistent through time, from one thing to another, that's going to show up in my differences between two. It's hard to, you can't really separate those out. You can get an idea, right, of whether they're concordant. Now, the more repeated assessments you do, that'll go away, right? So if I have Mario do this test 5 times, probably be better than doing it 2 times. I'm just setting you up for success. I'm not trying to make you do more work. You're like, good. Well, can you imagine assessing 100 items? Did I tell you about the time I made the assistant brewmaster smell over 1,000 cans? The sniff test, I didn't tell you that? And he almost passed out. We had to stop the test. It was one of these types of studies. He was the gauge. And I don't think I'll even go into that tonight. But that was fun. It's something August Bush wanted. I'm like, okay, you want this? You got it, buddy. And then we finally just stopped the test, and he called August and said, we're not doing this. And that was the end of that story. Okay, it was a great story. But then I was like, okay, you got to sit down, Steve. It's okay. What we're going to do with concordance and validity assessment is we're going to use, we have to use the modal response. And you're like, finally, we get to use the mode. I'm sick of using the mean. I'm sick of using the median. Now we're going to use the mode. I knew that you were waiting for the chance, and here it is. We're finally going to get to use the mode as our, are you so excited?
Very excited.
I know. Just finally, it's like, oh yeah, it's great. Okay, so we're going to use the most frequently occurring response, and because of that, because we want to use the mode, we want to have 3 or more repeated assessments in here too when we're doing our concordance and validity. We'll walk through how to do that. Probably won't get to it this week, but next week for sure. I know you're excited. The mode. All right, so here's a procedure. The first thing we're going to do is get items that are capable of being repeatedly assessed and marked in a non-obvious way so that we can't memorize what the samples are and then try to subconsciously mark them the same the next time. Pick 1 or more appraisers, and then you'll each of these items is going to be assessed in a random order by the first appraiser, and then the first appraiser is going to do it again until you get done with your desired number of assessments. And then the next appraiser will do the same thing. But you want to make sure The internal consistency, the concordance study time between readings is small. So concordance is between, right? So if I'm doing this study, I want to have Shane and Mario and Afton do it like on the same day if I could. Right, so just in case something changes with the samples, or maybe I have them in a room and they're doing a visual assessment and a light bulb goes out the next day. Just think of things that could happen that would affect your measurement validity. Okay, so concordance study time would be small. Internal consistency study time between readings long enough to avoid carryover bias effects. So if you had 100 items, and it's possible that people can remember what different items look like and how they assessed them. It's possible. It's not likely, but it's possible. So you might want to give them kind of a little break and then let them go back and do it. Just some things to think about for validity of your study that we talked about. So then we repeat the assessment, analyze the data, and then report the results. Easy enough to do. Okay, so the guidelines for this really similar to continuous data. You got to have training. If you have a certain location you want people to look at, then you've got to tell them what that is. Hide the identification of the items. Repeat the assessment. Select samples across the expected range. It's good, good or bad. It has to be representative of whatever your target population is. So all these things in here, just be cognizant of things that might be going on. So my recommendations are to make sure you have 2 or more appraisers if it's a visual assessment, and then at least select 100 or more items, and use approximately the same number in each category or representative based on what you produce. So if you want to do an equal assessment, do that first, but before you say, if you're doing a capability study, okay, if you're doing some type of assessment between appraisers, this is okay, but if you're doing a capability study, gosh, I can't spell tonight. Come on, Wendy. I want you to do this, okay? So this is okay, but if you're doing a capability study, it needs to be representative based on what you produce. And if it has to be some type of, especially if it's some type of external gauge and not a person, especially. There's some things that kind of sort, there's some gauges that say this is good or bad, and they kick stuff out here and there. That's especially important for that. All right, so those are the 3 repeated assessments by each appraiser. Ready to try some of this out for fun? We'll start with something easy. Ready? Here we go. 2 inspectors and 2 categories. What? It's Eddie and Harold again. Let's take a look and see what Eddie and Harold are doing. So they're going to look at 200 units off the line and assess whether it's okay or not okay. I don't know what the units are. What should the units be? Let's say the units are donuts. And there's some visual assessment for the perfect donut quality. And they're saying it's either okay or not okay. Any flavor donut you want?
Apple filled.
Apple filled. Trying to bring this example to life, okay? All right, so we've got Eddie and Harold, and you'll notice that you have these files available to you. Let's do this, okay? This is on, oh, it logged me off. Well, how dare you? Okay, so if you're looking for Eddie and Harold, this is the file. Click on that and then click download here. Okay, it's not a video. I don't know why it says that it thinks it's a video. No idea. So I'm going to pull up Eddie and Harold. File, open. Eddie and Harold. Ooh, they're looking at radio stuff. All right, let's see here. All right, so I've got them pulled up. You see a bunch of 1s and 2s, right? If you scroll down, everybody have that same stuff, and it should go to, should be 200 rows. This is a random measuring order, I suppose. Okay, now what I'm going to do is go to tests and crosstabs. It'll say table size 40,000, continue. Just go ahead and push yes. We're going to fix that here in a minute. First thing to do is click on File Data. And in my column for number 1, let's see what I'm going to pick. My column is going to be Harold. So click on Harold. Just push continue, yes. And then my rows are going to be Eddie. Do you get something like this? Good. So let's make sure that matches what we've got over here, and it does. And all I have to do is click on Kappa. I'm also going to, I'm going to click on Kappa for this one. Right, so this is how I get the results, and let's talk about what those results actually mean. So that's easy to do, right? You can just pull that into crosstabs. So here are the results. So we're going to look down here first, and I've got a p-value. And my hypothesis, my null hypothesis, is that kappa prime is equal to 0, and alternatively, kappa prime is not equal to 0. And so I've rejected the null hypothesis. There is significant agreement above that due to chance, right? Above that due to chance agreement. And so I have some data here. Here's my overall proportion agreement. So I've got 180 out of 200, that's 90%. It's my proportion chance agreement based on how the marginals turned out. The max that I could have gotten is, and sometimes your proportion agreement ends up being higher than that, so don't worry about that. This is my kappa right here, and I have a confidence interval. So kappa could be 0.688 up to 0.815 or down to 0.561. So this is the proportion agreement, so 69% agreement above that due to chance and chance alone. Okay, so I'm comparing two people. Is that internal consistency or is that concordance? Concordance. Okay, good. Okay, so we're looking at concordance. I concord with you, Harold and Eddie. All right, so here's another question. What if, here's a question here. Do Eddie and Harold classify their radios the same way after some time has passed? And this is a question of internal consistency. So Eddie could measure one time, and then Eddie could measure another time. And I want to see if there's going to be some differences. Now, what are the implications to concordance if internal consistency is called into question? They may actually not be concordant. Possibility. So if I don't agree with myself, the possibility that I'm actually agreeing with somebody else, I might be agreeing with them on the average, but it's possible that that was subjective. If I'm not stable through time, it's hard to say what I'll agree with next. Just throwing it out there. So there's some implications for concordance. You really want to have internal consistency before you start looking at concordance. So I'd want to make sure whoever my assessors are, that they're stable through time. So what we do for internal consistency is we look at McNemar's test of change. And I know you're excited of doing a dependent measures type of test, because when was the last time you got to do this? A long time ago, right? at 5005 whenever you took it. And I know you loved it when you did it, and now you get to do it again because now it's actually applied in this way, right? Like, oh, okay, I can use this to attest for internal consistency. So if I ask you on an exam, what was their internal consistency, you're going to come back to me and be like, wow, they don't agree with themselves, or they do agree with themselves, and you're going to give me some type of recommendation, right? Just telling you what you're going to do, because I know that's what you would do. All right, so we're using this for repeated pass-fail assessment on the same items, and so we're testing the hypothesis that the items they passed the first time and failed the second, the items they passed and failed are equivalent to the fail-pass ones, right? So we're looking at these before and after conditions. And we use this 2x2 contingency table. And so we only use B and C cells. You don't have to put anything in A and D. And we use this for testing for differences in repeated assessments.
So this basically helps us for internal
Yes.
or not. So McNemar will actually help us to detect that.
Mm-hmm. Exactly. If the test of change is significant from here to here. Because I'm looking at, these are the things that change from one time to the next, right? So the first time I said, this is before, the first time I did it, I wouldn't say this is before condition, after condition. I'll say this is first measurement, and this is second measurement. Let's just take that out, that's confusing. Right? So the first time I said this proportion of items passed and this failed, I agreed on those between the first and second time, but I changed my mind on this one. The first time I said it passed, the second time I said first time I said it failed, the second time I said it passed, right? The second. I changed my mind. So these are the items I changed my mind on. But has it changed significantly enough that it's significant? You know, let's say I only like maybe one or two items I kind of changed my mind on. Based on the number of items I assessed, I might expect a certain amount to be in those cells. But we're seeing, okay, did it change too much between one to the next? And if it did, if it's significant, then guess what? Something ain't right. So what we do here is we just click on this right here. So I could look at, this is Eddie's internal consistency. Let's look at MVP stats. I think we can do it in there. This one I don't think has it in there actually. Let's find it. Let me keep this. Let me see if I have this out. I don't think I have this available for you out there. How dare I? Oh, I have Eddie internal consistency for me. Did I not give that to you? Well, that's not very nice. Should I just throw that out there really quickly? Sure, why not? All right, here's data files. I have these in here. They're all zipped in this file right here. If you downloaded them, they are in there, but just to make life easier for you. Oops, I don't want to move the homework answers over. You're supposed to say, yes, you do. Data files, let's say files. Let me just move these over quickly so that you can follow along with me. Here's Eddie internal consistency and Harold internal consistency. Okay, so those are out there under discrete data introduction and data files if you want to grab those. I'm going to pull up Eddie, and you'll see here's Eddie, first iteration and second iteration. And I will go ahead and pull that up. Let me give you a minute to download it. Why don't I do that? Do you know that we have 2 classes after tonight? Yeah. Did you
We'll
think
have class next week, do we?
you don't have class next week? What are you going to do? Homework 5 and binary. Okay, you got it. We've got our iterations here. So I'm going to put in the columns, second iteration and first iteration in the first here. And then I'm going to click on McNemar's and Kappa. I don't really need Kappa in there, but I'm interested in here. And so you'll see that there is a significant change for Eddie. So that tells me he's not internally consistent. That's his first iteration. He called these items both in second and 1, but these items over here, the first time he passed them and the second time he failed them. And then over here, the first time he failed them and the second time he passed them. Ruh-roh. Either way, that's a problem, right? Okay, so I can see that's what I'm looking at for Eddie. Okay, and I could then I could do the same thing for Harold out there. I won't make you do that at this point, but I'd absolutely do it. What do you notice about the difference between Eddie? Oh, I had it backwards. No, close. Same thing. And Harold for the B and C cells. Yeah, he's consistent. Now, that doesn't mean he's consistently right, but he's consistent, right? That's the thing, is that we'd have to compare, do some concordance studies with the standard. You could be consistently wrong, and that person's probably more trainable than the one who's not consistent. All right, so we see there's some conclusions here associated with Harold and Eddie. So Harold is consistent with himself, and Eddie not so much. And so we compared them with, internally, and this is what we would do. First, compare internal consistency. Then next, you would do concordance with each other. And then, finally, concordance with a standard. Think you could do that? It's an easy one. It's a really easy one. Okay. Want to do 2 appraisers more than 2 categories? Okay, we've got like 8 whole minutes. I think we could get this part done. All right, we've got Mike and Peg. Like I said, those were consultants, and they are working on the hotline at some aluminum company. One of the critical activities is the assessment of the background pickup off the hotline for rolled aerospace product, and so this is some type of defect that they really don't want to have. So they're thinking about renovating this line. They want to make sure this characteristic can be adequately assessed. If the assessments are unreliable, process changes cannot be evaluated appropriately. So here's what they're going to look at. So there's some type of rolls, and you roll across. If you've ever been part of a rolling process, sometimes you can pick up things like this. Of course, you all have had printers at home, and you've ended up with these types of defects from your rolls, right? And a lot of it has to do with roll wear and picking up and cleanliness of. Every once in a while, my printer decides to clean itself. Anybody else have a printer like that? Okay, you know what I'm talking about with printer services. You just kind of like, I don't really understand. I just want it to print my stuff. Really, that's all I want. I don't want to see chunky. I don't want to see streak. I don't want to see light. I don't want to see any of that. I just want it to work the way I want it to work so I can read it. All right, so here's one. So they've got 500 test panels selected from production using a stratified random sampling approach. So they probably took things from different lines and different processes. And they've got 300 test panels determined by consensus to be free of background pickup. So they could have had an expert panel of judges, people who have been doing this a long time. And they all say, okay, yep, we all agree that there's not background pickup. And then 200 of them were saying, yep, they've got some background pickup of some type. Now let's test our raters to see if they can figure out how to assess these things. So here's the categories. It can be acceptable or unacceptable. And if it's unacceptable, they have to categorize it into chunky, streak, or light. So first thing, let's take a look at Mike and Peg's degree of agreement on acceptable and unacceptable. So here is, and so what we're going to do is collapse across this, and I need to show you how to do that, because it's not clear in here. So let me show you this. Is there a file out there called Mike and Peg? Let's pull that one up. Mike and Peg. So we've got Mike and Peg. We're not doing internal consistency assessment on this one. Did you just raise your hand? Okay, sorry, I just picked up something in my peripheral vision that did not happen. It snowed here tonight, Jeff, so it could be why I'm seeing things.
Yeah, it's supposed to snow here on Sunday, so you guys beat us.
Yeah, it's coming your way.
Yep.
Okay, so go to crosstabs, and you'll see that we have, let's do columns. Let me look at how this is set up here. Peg's on the columns, Mike is on the rows. So let's make sure we set it up the same way so it looks the same. So here's Peg, here's Mike, and you see I've got all the different categories across here. I just want to see okay and not okay. So what I have to do is select Peg 2, 3, and 4. So hold down your Shift key. Select Peg 2, 3, and 4, and see this thing that says merge? Merge. And then I'm going to do the same thing on the row. Click on Mike, hold down the Shift key, 3 and 4. Merge. Did it work? Okay, Mario, did it work?
The merge button. What?
Okay. Here, remove. Oh, didn't want to do that. Start over.
Welcome.
Peg, Mike. Okay. So when I select this, I hold, see how that comes up? Does that come up for you? What? Did you click on the column or did you click in here?
There.
Okay, don't click in there. Click on the title.
There you go.
Yep.
Merging now.
Now it's all about merging. Okay. All right, now I can make some comparisons, right? So I'm going to click on just Kappa here. And I can see my proportion agreement. I can see that it's significantly above chance and chance alone. My confidence intervals between 98 and 100% agreement. Hey, that's pretty good. Okay, so I'm looking at this and I'm like, oh, okay, well, they're doing a pretty good job here associated with putting things in agree and not agree. All right, now, because see, I see here and I say, all right, they classified these as good ones. They both say they're good. They both say that these are bad in here. But now I want to look within the categories of bad, because there could be some disagreement among the disagreement of what we say is unacceptable. I know. 2 more minutes. Hang with me here. 2 more minutes, and then we'll pick this up again. So let's take a look here. So look at the panels classified unacceptable by both and see how well they agree on the reason. Okay, so overall, they agree that these are unacceptable, but let's see what they have to do with the reason. So let's take a look. And I'm going to go back here, click on this. Oh, I guess you can't merge it a second time, but you could just go back and click on Peg again and click on Mike again in the rows, and it clears that out. Now I'm just going to go ahead and get rid of row 1. That's the agreement row. Just push remove. and then peg, remove. And now what is left over is the unacceptables. Now we have to see if there's agreement associated with that, above that due to chance and chance alone. Okay, so we're looking at we're looking at these categories. So we've got, so this is what we're looking at here. The 150, Mike and Peg agree on that for category 2. What do we say? They're chunky, streak, and light, right? 2 equals chunky, 3 equals streak, and 4 equals light. Here's where they agree, right in this diagonal, correct? Okay, so 150 plus 28, that's 178. So out of those 200 that are left, they agree on 178 out of 200. Right? So the rest is disagreement. And looks like our agreement here, let's see, our Kappa value, 0.677. What was it on okay, not okay? 0.992. So our agreement was better when we're just looking at okay, not okay, as opposed to the reason why it's not okay. So again, we're looking at agreement within the unacceptable category. And I think that I've sufficiently worn you out tonight. You did a great job. We're on slide 60. We'll pick this up next week, and I'll have a binary for you to earn some extra credit, which is almost unheard of in graduate school. So I say that, I'm sure that there's plenty of extra credit. All right, have a great fall break, and I will look forward to seeing you when you get back. I hope that you are able to at least get some rest and have at least one day of fun. Promise me you'll do this. Just one day. I'm talking to the overachievers here.